Welcome to Study Loop.
Okay, so for this problem, we're given a velocity vector as a function of time. And for part A of the problem, it's asking what are the x and y components of the car's velocity, or what are the x and y components of the acceleration? So what we need to do is we need to take the velocity function and calculate acceleration. So in order to calculate acceleration from velocity, we just take the derivative of the velocity. Okay. So we want the x and y components of acceleration. So we want ax. So we'll calculate ax first. So all we do now is take the derivative of the x component of velocity to get the x component of acceleration. Okay. So we have d dt of vx. Okay. So derivative of the first term of vx is going to be 0 because it's a constant. And let's look at the second term here. So the derivative of the second term is just going to be the coefficient here, which is 0.018. And that's going to be times the derivative of t squared. Well, the derivative of t squared is just going to be 2t. So it's going to be the 0.018 times 2t. And there's going to also be the minus out in front here. Okay, so we have this. And we're going to keep the units here. So we're going to keep the meters per second to the third. Okay. And then we can multiply this through. Okay. So it gives me the x component of the acceleration. Now for the y component, so I'm calculating a y now. I'll take the derivative of the y component of velocity. So I have d dt of vy. Okay. So look at the y component. The first term, 2 meters per second here is going to be 0. It's constant. And the derivative of 0.550 times t is just going to be 0.550 because it's a coefficient in front of t. So my derivative is going to be 0.550 meters per second squared. So that's going to be my y component of acceleration. Okay. All right, so now for part B, so this is part A. Okay, so now for part B, it's asking what are the magnitude and direction of the car's velocity at t equals 8 seconds. Okay, so we want to find the velocity at t equals 8 seconds. So all we have to do here is use the velocity function and plug in t equals 8. So if we do that, we'll get the velocity for the x direction and y direction. So if we look at the x direction first, so we have vx here. And then we'll plug in t equals 8 in the vx equation here. So that we get a result for vx at t equals 8. So we plug in t equals 8 for vx. We're going to get 3.848 meters per second. And again, all I'm doing is plugging in t equals 8 in the I component here. So that gives me vx. Okay. And I'll do the same thing for vy. For vy, I'll look at the j component here, and I'll plug in t equals 8, and that gives me the result for vy at t equals 8. So if I do that, I'm going to get vy is equal to 6.40 meters per second. Okay. So now it's asking for the magnitude and direction of the velocity. So the magnitude, I'll use the magnitude equation here. Okay, so I know what vx and vy are, so I'll plug in the magnitude equation and get my v. So I plug those in, I'm going to get 7.47 meters per second. So that's going to be my magnitude. Okay, now what about the direction? Well, for the direction, I can use an equation for theta. So theta is going to give me the direction. So for theta, I'm going to have arctan of the y component of the vector. And our vector in this case is going to be v. So I'm going to have vy divided by the x component of the vector. So it's going to be divided by vx. So now I can plug in vy and vx in this equation. So if I do that, I'm going to get the angle theta here is 60 degrees, 60.0. That means the velocity is in the direction of 60 degrees. Okay. And then part C, it's saying what are the magnitude and direction of the car's acceleration at t equals 8 seconds. Okay. So now what we do is we look at the x and y components of acceleration, which we already have from part A, and then plug in t equals 8. So I'll plug in t equals 8 for the equation of 8x from part A, and then I'll get my result. So I plug in t equals 8 in the equation for ax. I'm going to get negative 0, negative 0.288 meters per second squared. And I'll do the same thing for ay then. So I'll look at the equation for ay, which is 0.550 meters per second squared. So in this case, there's actually no t to plug in here because the equation doesn't have a variable t. So my ay is just going to be the result that I calculated from part A, because it doesn't even depend on time. So it's just that value then. So if I don't have a t to plug in, I just use the value I calculated from part A. Okay. And again, I'll calculate the magnitude of the acceleration by using the magnitude equation. Okay, so I just plug my value for ax and ay that I just calculated here. So now I'm going to get a value of 0.621 meters per second squared. So that's going to be the magnitude of the acceleration. Okay, and then I'll calculate the direction now. So I'll start a new page. So the direction is going to be arctan. In this case, my vector is a. So I have the x direction of the vector, so I'm going to have ax divided by the y direction, the y component of the vector, which is ay. Okay, so I'll plug in my ax and ay value. And then I'm going to get an angle of 117.6 degrees. So then that's going to be my direction.